Armed and prepared, South Vietnamese Air Force F-5s embark on a strike mission. These aircraft were designed to meet very specific needs. They had to be small, light, and inexpensive. They were the first weapons system created by the U.S. government to fit the requirements of the Military Assistance Program. These aircraft were meant to be provided to the United States' smaller allies. More than 20 nations used them. They were the Northrop F-5 Freedom Fighters. The F-5's development defied the prevailing fighter aircraft trends. Other manufacturers were creating larger and more complex planes. After Korea, financial backing allowed the U.S. to focus on advancing technology. New avionics, missiles, and engines drove the increase in fighter aircraft size. However, Northrop took a different path. Northrop's design team researched the core aspects of fighter aircraft and identified key general requirements. In their view, the most critical of these was keeping the aircraft small. In a classic case of successful innovation, this reprisal led not only to the F-5 family, but also had a far-reaching impact on fighter aircraft development. The role it was designed for was modest, but Northrop's little masterpiece was anything but. It proved to be a maneuverable and highly effective weapon. These planes are F-5Cs, a rare variant. 19 F-5s were re-equipped for U.S. Air Force combat trials in Vietnam. Due to these modifications, they received a new designation and became widely known as the Scotia Tigers. After their service with the U.S. Air Force, the modified planes were transferred to the VNAF, making them South Vietnam's first modern jet fighters. Over time, around 200 F-5s were operated by the Vietnamese. The combat use of the freedom fighters in Vietnam confirmed their effectiveness, highlighting the significant impact they had on a small nation's Air Force capabilities. Orders flooded into Northrop, and F-5s were distributed worldwide. In action, the Vietnamese pilots' aggression paired well with the aircraft's precision, especially in ground attack roles. The F-5's payload was small, but its accuracy compensated for the lack of size. The F-5's successful deployment in Vietnam reinforced the value of Northrop's innovative design. The design team's focus was vindicated. The planes were simple and easy to maintain, and their reliability gave them an advantage over other models. They achieved the highest operational readiness with the fewest maintenance hours. The F-5's ease of control, stability, maneuverability, and precision made it a favorite among pilots. Unfortunately, it saw limited air-to-air combat, so its exceptional dogfighting agility was not fully showcased. It would take another decade after Vietnam for the lightweight fighter's merits to be widely acknowledged, ironically, particularly in the US, where the freedom fighter was developed. The F-5's origins trace back to 1955, when Northrop completed its initial fighter studies. They created the N156 design as the foundation for a supersonic trainer or lightweight fighter. The U.S. Air Force showed little interest in small fighters, but the design's appeal as a trainer couldn't be overlooked. On June 15, 1956, approval was granted for the production of prototypes, which would later be known as the T-38 Talon. On April 10, 1959, the first T-38 flew, beginning a test series noted for its smooth progress. It became the first supersonic aircraft to complete testing without a major accident. There were no aerodynamic issues, and the plane demonstrated no problematic traits. The T-38 quickly earned a reputation for exceptional handling and forgiving flight characteristics. Following the success of these initial flights, larger orders came in, and by October 1959, production increased from 2 planes a month to 10. Ultimately, nearly 1,200 T-38s were built. Meanwhile, Northrop continued developing the fighter version at its own expense, targeting the market of less affluent American allies. It was a calculated gamble, but a well-informed one. U.S. defense officials recognized the logic of supporting allied nations with modern equipment. It was more practical to arm them with capable, modern weapons than with outdated hand-me-downs. An ally equipped with obsolete technology offers limited support. In May 1958, Northrop was authorized to proceed with building 3 prototype N-156 fighters. Established T-38 tooling sped up construction, allowing the first aircraft to fly just 14 months later. Despite the success in testing, the U.S. Air Force had no interest in a small fighter for itself, and no development program existed for foreign use. As a result, only 2 prototypes were completed. The partially constructed 3rd prototype was placed in storage. For a while, the U.S. Army showed great interest in the N-156F for ground attack and close support roles. In competition with other aircraft, the N-156F demonstrated remarkable performance, along with its reliability and ease of maintenance. However, the Army's competition was ultimately canceled. The Air Force closely guards its responsibility for operating high-performance land-based fighters, and thus, for the Freedom Fighter to enter U.S. service, it would have to be operated by the U.S. Air Force. Since the Air Force had no interest in the plane for itself and refused to let the Army operate it, the N-156F project stalled. Northrop remained confident in their aircraft, and everyone who encountered it was impressed. However, there were no buyers. It wasn't until May 1962, almost 3 years after the first flight, that the project finally saw success. The Department of Defense had continued evaluating the needs of U.S. allies in NATO and SEATO. The standard practice had been to supply the poorest nations with aging U.S. jets that were obsolete by Air Force standards. This was an inefficient use of Allied defense resources. What was needed was exactly what Northrop had designed. The Kennedy administration, committed to maintaining global freedom, pledged to actively re-equip Allied forces. Northrop's plane was the only serious U.S. option for a lightweight, low-cost fighter. It was thus announced that the N-156 had been selected as the defensive aircraft to be provided to favored nations under the Military Assistance Program, MAP. In October 1962, the program was formalized, and orders were placed for 2 versions of the N-156F, a single-seat fighter and a twin-seat version that could double as a trainer. These received the U.S. Air Force designations F-5A and F-5B. The partially completed 3rd N-156F prototype, still in storage, was finished to meet the new specifications and designated as the YF-5A. The first flight of the newly developed plane occurred on July 31, 1963, with Northrop test pilot Hank Chateau at the controls for a smooth, incident-free flight. As with the T-38 and N-156 trials, the testing program proceeded without issues. Modifications to the original design were minimal, primarily involving more powerful engines and an increased weapons load. Additionally, the aircraft received more rugged landing gear for rough terrain. Despite these upgrades, the F-5 remained much smaller than other contemporary fighters, about 1/3 the weight of an F-4 Phantom. The key to the F-5's size was the choice of power plants. Northrop's designers quickly recognized the potential of small turbojets originally developed for missiles. They saw an opportunity to achieve significant savings in thrust-to-weight ratio while incorporating the safety benefits of a second engine. The two engines were positioned side by side in the aft fuselage. Each F-5 engine weighed only 570 pounds, including the afterburners, yet produced 4,080 pounds of thrust. With a straightforward two-point mounting system on built-in overhead tracks, maintenance was incredibly efficient, allowing a crew of 3 to remove and replace an engine in just 20 minutes. A key aspect of Northrop's concept was simplifying maintenance, and the design featured many elements that directly supported this goal. Additionally, the aircraft was designed with minimal complex avionics and electronics. The very high operational readiness of the F-5s can be largely attributed to the ease and simplicity of ground handling and overhaul tasks, particularly when compared to other supersonic aircraft. A total of 8 aircraft were utilized in the development and flight testing program, quickly followed by production models. Initial deliveries to the U.S. Air Force Tactical Air Command took place at Williams Air Force Base in 1964, where U.S. air and ground crews trained on the aircraft. These personnel were tasked with instructing foreign servicemen in the maintenance and operation of the plane. Each military assistance program, MAP country, receiving the F-5 would send a group of pilots and specialists for a training course with the goal of returning home as qualified instructors. Although the F-5s used in this program bore U.S. Air Force markings, they were actually owned by the respective countries. The first training classes commenced in September 1964, with crews from Iran and Korea participating. U.S. pilots from the Military Assistance Advisory Group also participated in this course. Their role was to advise F-5 customers on effectively integrating the new aircraft into their inventories and employing them in the field. The F-5B two-seaters had also completed testing successfully and began to be delivered. Equipped with dual controls, the instructor pilot could take over if needed from a position well above the forward cockpit. In addition to their training capabilities, these planes also served as attack aircraft. Considering the limited resources of many client nations, the aircraft was designed to handle rough terrain and basic or non-existent landing facilities. The ruggedness and stability of these small planes were best demonstrated in such operations. Limiting the sophistication of the F-5 may have affected some performance aspects, but for its customers, it was the only viable option. They found it ideally suited to their capabilities and budgets, providing them with a highly effective defensive and offensive strike platform. For most of these air forces, it marked the first time they had deployed modern combat aircraft. One of Northrop's significant challenges in scaling down a fighter was ensuring compatibility with existing weapons in the inventory. Special attention was required in designing smaller aircraft, as standard items like stores, pylons, and ammunition belts are relatively large in proportion. The bulk of these common systems ultimately establishes a minimum practical size for the aircraft. The F-5A was armed with 2 nose-mounted 20mm cannons, carrying 280 rounds of ammunition for each gun. As with all aspects of ground handling, the procedures for accessing, clearing, loading, and arming the guns were straightforward. allowing everything to be reached easily by a crewman standing on the ground. This built-in maintenance simplicity also applied to tasks such as aiming the guns. With minimal skill levels and just a few simple tools needed, this was established with little difficulty. The guns themselves were rapid-firing, capable of delivering 1,500 rounds per minute. A short burst from the two cannons could inflict significant damage. Additionally, Sidewinder missiles could be mounted on the wingtips, giving the small fighter a formidable air-to-air capability. Thanks to the F-5's stability and ease of control, impressive accuracy with the cannons was attainable. Although the twin-seat B model did not have a nose cannon, both versions featured 7 external store stations. These stations could accommodate a wide range of tactical ordnance and fuel. Missiles, bombs, napalm, and rockets could be carried in various combinations as required for a mission, with a maximum load capacity of up to 6,200 pounds. As a tactical support weapon, the F-5 consistently proved its value in the field. The combination of excellent high and low speed maneuverability, unrestricted visibility, rapid response time, and stability made the F-5 an outstanding close support and interdiction fighter. Upon its introduction in 1964, the F-5 made a significant impact, capturing 85% of the weapons meets it entered during 1964 and 1965. These formal competitions, held both in the US and abroad, pitted the freedom fighter against various top frontline fighters from the West. This small aircraft embodied qualities that made it a formidable opponent. The initial orders placed by the Defense Department in 1962 totaled 71 F-5As and 15 F-5Bs, with many more orders flowing into Northrop in subsequent years. The first F-5s were activated by Iran in February 1965, and by the end of that year, another 5 air forces had received the new planes. Additionally, several significant orders had been placed for F-5 production. The aircraft was so impressive that several non-MAP countries decided to purchase it independently. As early as 1964, agreements were reached with Norway and Spain, the latter including provisions for licensed production. In 1965, Canada also decided to purchase the Freedom Fighter, again opting for production in the customer's factory. Each year saw more countries joining the growing list of F-5 customers. The concept of area ruling was applied to the aircraft developed by NASA, which posited that the cross-section of the entire aircraft should vary smoothly along its length. The waist added to the fuselage above the wing acknowledged the additional forward-facing area of the wing itself. This area ruling contributed to the F-5's slimmed hips and the overall smoothness of its design, extending even to the wingtip fuel tanks. While the F-5 had its limitations, they were offset by the power and sophistication of the weapons it could carry. Armed with Sidewinder missiles and cannons, it was a dangerously effective interceptor. Additionally, a new role was developed for the aircraft with the introduction of a camera pack, which, combined with external fuel storage, transformed the F-5 into a long-range reconnaissance platform. In its primary tactical role, the F-5 could carry 4 large bullpup missiles or up to 76 rockets, providing a formidable ground attack capability. All fuel storage, both internal and external, could be pressure-filled in minutes from a single fuel inlet, exemplifying the design's emphasis on simple maintenance. Over a quarter of the aircraft's surface consisted of hatches and removable panels, facilitating easy access to its equipment. This accessibility was further enhanced by arranging components one deep in the fuselage, allowing for straightforward servicing of all major parts. Special testing equipment was minimal, designed to be rugged, portable, and simple to operate. Compared to other aircraft capable of similar operational missions, the F-5's maintenance requirements were minimal, marking this aspect of its design as a total success. The F-5's load was nearly 50% of its weight, resulting in the highest payload-to-weight ratio of any supersonic fighter. Thanks to the aerodynamic efficiency of its shape, the F-5's small engines were able to propel the fighter at approximately Mach 1.3. Its supersonic capability was limited not by the airframe, but by the turbojets, which drew criticism for their performance. However, since these engines were key to the aircraft's compact size, this compromise was unavoidable. Recognizing the design's potential in the close support role, the U.S. Air Force decided to trial the planes under combat conditions in Vietnam. In what was known as Operation Scotia Tiger, 19 aircraft were re-equipped to USAF standards in 1965. These modified planes featured an aerial refueling system, armor plating, and jettisonable pylons, and were designated as F-5Cs. They arrived in Vietnam on October 23rd and flew their first combat mission within hours of landing. During the 150-day evaluation, the Scotia Tigers completed more than 3,500 sorties, carrying an average combat load of around 2,500 pounds. Most missions were conducted using 500 or 750-pound bombs, although a variety of ordnance was delivered. The types of missions included close support, interdiction, armed reconnaissance, escort, and MIGCAP. The F-5s won over their pilots and impressed ground troops with their stability, accuracy, and reliability. Remarkably high readiness rates were achieved, and by the end of the trial, practice had reduced maintenance per flight to just 6.5 hours. Northrop had initially expected maintenance to require 21 hours, a figure that would have been reasonably acceptable. The mission abort rate was also impressively low at only 1.5%. Given this evidence, the U.S. Air Force once again reassessed the F-5. The outstanding performance naturally pointed to the need for an advanced version to address lingering concerns about engine power, range, and payload capacity. As a variation of the F-5A and B, newer and more powerful engines were incorporated. Additionally, many variations provided for individual buyers were re-evaluated, and any performance enhancements were integrated into the new design. This work began in April 1968, but was cancelled in late 1969 with the announcement of a new competition to determine a successor to the F-5 variant for the MAP program. Northrop's entry in this competition was the newly developed F-5 variant, shaped by the experiences of Vietnam. The F-5 was announced as its own replacement, leading to some confusion, and to recognize the changes in design, new designations were assigned. The single-seat version would be the F-5E, while the twin-seat version would be known as the F-5F. In the fall of 1971, it was also announced that, in honor of the Scotia Tigers and their influence on the successful design, the aircraft would be named the Tiger II. Given that Scotia is Japanese for small, the full title would have been fitting, as the F-5s were certainly small and tiger-like in their capabilities. The rollout of the new plane took place on June 23, 1972, followed by its first flight on August 11. Progress up to that point can be easily measured. During 8 years of production, over 1,100 A and B models were manufactured for service in the air forces of more than 20 countries. Northrop's small fighter had transformed into a major sales success. The F-5E's engines produced 5,000 pounds of thrust, representing an increase of over 20%. However, some of this additional thrust was offset by the aircraft's increased weight. While the new version boasted more power, experience would reveal that it still fell short of fully exploiting the airframe's capabilities. When lightly loaded and at full throttle, the E could achieve Mach 1.6, but it performed more comfortably at high subsonic speeds. The Tiger airframe was fundamentally the same as its predecessors, with a slightly wider fuselage and several refinements to its shape. The original design had been so effective that minimal alterations were required. The fuselage was constructed entirely of metal, featuring a stressed skin semi-monocoque structure. While some steel and titanium were used in the aft fuselage, the majority of the aircraft was riveted aluminum. The wings were designed as a single piece, spanning from tip to tip. This design choice eliminated splices in the heavily loaded components. With the exception of steel ribs that supported the landing gear and wingtip store stations, the entire construction was made of aluminum. The wing skins were primarily shaped using chemical milling methods. The aircraft's combat capabilities significantly advanced with the addition of a fire control radar system and a computer gun sight. This system enabled target detection, range tracking, and lead computation for the cannon, as well as range envelope calculations for the sidewinders. Air-to-ground delivery was also improved with roll-stabilizing aiming references. Several modifications were implemented to enhance takeoff performance, including air doors to increase airflow and a 2-position nose gear that added 3% to the angle of attack. With these enhancements and the engine's added power, takeoff performance improved by 30%. Remarkably, Northrop was able to retain 75% of the tooling masters from the earlier models despite these and other changes. In service, 40% of the spare parts and 70% of the ground support equipment remained unchanged. Early F-5Es featured interchangeable nose sections, allowing for the installation of reconnaissance configurations. In 1978, however, a specialized reconnaissance version was developed, featuring a lengthened nose and various load options. This included not only cameras, but also side and forward scanning infrared equipment, along with other highly effective and sophisticated modern surveillance and search electronics. Loaded in pallets, the chosen configuration could be quickly installed to meet any mission requirement. The reconnaissance version, named the Tiger I, retained its sidewinders and a single cannon. Development was funded by the company and resulted in a highly competent specialist aircraft. Northrop's innovative small fighter had now evolved into a family of planes. Production transitioned smoothly to the new model, with the first F-5Es being delivered by the end of 1973. By 1976, Northrop's sales of T-38s and F-5s had exceeded 3,000, with ongoing orders for Tiger IIs. T-38 production ended in 1972, with the U.S. Air Force receiving the last of the 1,189 aircraft produced. Production of the Tiger II continued for another 17 years, with the final E and F models delivered to the Singapore Air Force in 1989. The total number of T-38 and F-5s manufactured reached 3,806. The T-38 Talon became the only variant of the aircraft widely adopted by the U.S. Air Force, with a total purchase of 1,139 units. In 1974, a decade and a half after its inception, it garnered further acclaim by being chosen as the aircraft for the Thunderbird's display team. This replaced the larger F-4 Phantom, allowing the T-38 to showcase its signature precision and agility. Furthermore, the team discovered they could operate 4 Talons at the same cost of flying just one Phantom. The F-5E Tiger II would become the most successful model overall. It offered a variety of equipment levels customized to the buyer's financial capabilities, resulting in numerous sales beyond the Defense Department's MAP support. Some of these included advanced electronics packages for Saudi Arabia. The Saudi variant, equipped with inertial navigation, radar warning systems, chaff or flare dispensers, and Maverick missiles, proved to be a highly capable fighter. Reception for the Tiger II varied widely. Its merits were recognized, yet the aircraft did not secure a significant U.S. Air Force order. Once more, the F-5 was deemed insufficient in power. This limitation, dictated by the primary goal of maintaining a low aircraft weight, compromised the plane's exceptional maneuverability and flight handling. Throughout its operational life, many experts dismissed the F-5 due to the belief that it was so underpowered as to be constrained. This viewpoint overlooked much of what the Vietnam experience demonstrated. A significant amount of the accepted knowledge from post-Korea theory was upended in Vietnam and the Middle East. Fighter design was predicated on the notion of supersonic aircraft engaging in missile exchanges at long ranges. However, this proved unrealistic. In reality, very little aerial combat occurs at supersonic speeds or at extended ranges. Once planes join combat and begin extreme maneuvers, speed is rapidly lost. Once aircraft engage in combat and execute extreme maneuvers, speed is quickly diminished. Traditional dogfighting ensues, with planes in close proximity fiercely vying for superiority. In these scenarios, the F-5 can outperform nearly anything in the air. The U.S. Air Force inventory lacks any other aircraft that matches the F-5 specifications. The closest comparison might be the Soviet MiG-21. Although the MiG boasted a more powerful engine and could surpass Mach 2, this was its sole significant advantage over the Tiger. While the MiG is highly maneuverable, its service record has been mixed, with some variants proving hazardous. In direct confrontations, the two planes would be closely matched. The F-5's advanced avionics and weapon reliability would help level the playing field. Sales of the F-5E enhanced the capabilities of small air forces across the globe. Arrangements were established for overseas production, including agreements with Switzerland and Taiwan. Serving as the cornerstone of the military assistance program, it built upon the earlier model's achievements. A blend of low cost, high efficiency, and rugged simplicity was unmatched by any other U.S. design. The program significantly bolstered the strength of Western alliances. Throughout South America, the Middle East, and Asia, nations with limited economies saw their air power significantly improved. Interestingly, a notable number of aircraft were sold to Europe. These purchasing choices, much like the orders from Saudi Arabia, were not primarily driven by economic factors. Countries such as Norway, Switzerland, and the Netherlands are not economically disadvantaged. Instead, these nations determined that there was no need to invest in larger, more complex, and more expensive aircraft for roles that the F-5 could fulfill effectively. There was also one communist air force operating F-5s. Following the fall of South Vietnam, the North Vietnamese captured and utilized 80 F-5s of various models. These aircraft were later employed with significant success against Chinese planes during border skirmishes. The final iteration of the F-5 family was the F-5G. Over the long lifespan of the F-5, engines had advanced dramatically, offering more power from smaller and lighter designs. The aircraft was redesigned to incorporate the engine from the F-18, which produced 16,000 pounds of thrust. For the first time, the aircraft was equipped with adequate power, resulting in a remarkable enhancement of the F-5's capabilities. This marked the first major redesign of the aircraft, which was subsequently renamed the F-20 Tiger Shark. With ample power available, Northrop was able to integrate additional capabilities into the aircraft. Although larger than its predecessors, it remained a compact fighter, now capable of comfortably reaching speeds up to Mach 2. This was achieved without sacrificing any of the F-5's exceptional maneuverability and handling. The project began as a co-production initiative with Taiwan, but even though a presidential veto was placed on the Taiwan deal, Northrop continued to refine the aircraft until 1980. Surprisingly, despite the impressive capabilities and competitiveness of the Tiger Shark, it received no sales. It had addressed concerns about the aircraft's performance, its takeoff was exceptional, its electronic systems were state-of-the-art, and its price remained low for a high-tech fighter. Northrop ultimately accepted the absence of orders, leading to the abandonment of the Tiger Shark and effectively concluding the development of the family of small fighters. Over the years, the strengths of the F-5 and T-38 designs have led to these nimble aircraft being entrusted with various significant roles. Thanks to its two-seater configuration, speed, stability, and agility, it proved to be an excellent chase plane. It has played a vital role in some of the most important aviation projects in the United States. Notably, when the XB-70's tires ignited during landing, the pilot first learned about it from a T-38 flying alongside. Similarly, it was the T-38 crew who spotted fuel leaking from a broken seal on the space shuttle during one of its glide trials. The role of chase planes in a test program is an active one. They are not merely observers and recorders of the test aircraft's behavior. They maintain constant communication with the test pilot and can often provide insights about the aircraft that the pilot and his instruments cannot ascertain. Sometimes that information is critically important. From the start of its career, the T-38 and F-5 designs have consistently demonstrated impeccable handling and stability. They have always possessed enough aerobatic capability to satisfy even the most demanding pilots. NASA acquired T-38s for astronauts to help them maintain their flying skills. The small trainers have also found various roles within the U.S., including mission support with the Strategic Air Command, chase and test support for the Aerospace Research Pilot School, training for the Royal Air Force, and their service with the Thunderbirds. The F-5 also made a return in the X-29 program. Here, alongside a T-38 chase plane, the forward-swept wing X-plane is seen during its test series. The fuselage is based on an F-5 with undercarriage components from an F-16, combined with the innovative wing design that enhances maneuverability. The simplicity of construction, strength, and aerodynamic efficiency of the F-5 made it an ideal candidate for such a transformation. The X-29 serves as an experiment to shape the future of fighter aircraft. It is fitting that the F-5 plays a role in this initiative. Historically, most training exercises were conducted within similar aircraft types, meaning pilots practiced against the same kind of planes they were flying themselves. In actual combat, this scenario is one of the least likely to occur. To address this issue, the U.S. Navy developed a strategy known as DACT, or Dissimilar Air Combat Tactics. This has become more widely known as Top Gun training. Essentially, this program aims to replicate combat conditions as realistically as possible. Ultimately, the United States also acquired a supply of F-5Es, which had been designated for the South Vietnamese before their collapse. These 70 aircraft formed the foundation for the aggressor squadrons in the U.S. Air Force equivalent of Top Gun, known as the Red Flag exercise. Flown by some of the Air Force's top pilots, the F-5 squadrons represent a formidable force. The F-5s are utilized partly due to their similar characteristics to the MiG-21, with pilots training in Russian tactics, formations, and maneuvers. During the exercises, Nellis Air Force Base transforms into a combat deployment environment for the participating squadrons, complete with limited support facilities and the organizational challenges typical of a combat situation.
It's important because they find out what these planes can do in a wartime situation, and that's good practice for both the crew chiefs of the planes and the air crew.
Throughout their tenure in Red Flag, the F-5s have faced virtually every frontline fighter in the West. The aggressor pilots are highly experienced and have become specialists in Red Flag exercises. However, it is still sobering to note that against the best fighters the Western powers have deployed over the past 20 years, no aircraft type has demonstrated a clear superiority over the Tigers.
Copy that, and it's now 15036, still tracking north. Under contact now, 30 degrees left at 25. Split off to the north, Buck. You got one 225 for 13, and the other one is 5 miles north of him. Okay, I got the north guy. Watch for that guy to the other side there, Buck. Thanks. Roger, Buck. Okay, Fang, you go after the guy to the south. He's 230 for 10 coming at you. I got him. He's advancing to this side. Looks like we got some F4s north of Felicia Peak. We got the Bandits 150 for 40 miles. We may try to hit over that way. You headed south now. That's firm. We're steady about 170.
Okay, the lead just went in a right-hand turn to south. Come hard left, 180. Check on the nose a mile.
You got a bogey. 6 o'clock for 6,000 feet. Right. Keep the turn in. We're coming around hard on him. Okay, got it. Yeah. I'm going left. Somebody pick him up. Roger, he's off us. He switched. Reverse back. Come back left.
The opponents of the Tigers in these exercises are frontline squadrons equipped with the most advanced aircraft and trained to the highest standards. The electronically assessed kill ratios from Red Flag tend to favor aircraft like the F-15 and F-14, which are truly impressive systems when pitted against the F-5s. However, the margin is narrow. When comparing the number of aircraft shot down to the dollar value of those planes, the results change dramatically. The Red Flag exercises involving F-5s suggest that a force of Tigers would prevail with the margin against the equivalent dollar value of any other aircraft type, including much more modern designs. This not only casts the F-5 in a more favorable light, but also challenges many long-standing criticisms of this unique family of airplanes.
The McDonnell F-101 Voodoo was a supersonic jet fighter which served in the United States Air Force and the Royal Canadian Air Force. The origins of the F-101 actually had little to do with the jobs for which it was used over its long career with the U.S. Air Force, Air National Guard, and Canadian Armed Forces. Neither tactical reconnaissance nor all-weather interception had been a factor in early 1946 when the newly formed Strategic Air Command solicited proposals for a jet-propelled strategic penetration fighter. SAC's chief criteria at the time had been sufficient range to accompany its bombers, Boeing B-29s and the soon-to-fly Convair B-36s, all the way to their targets, and adequate speed and firepower to deal with enemy interceptors. 4 swept-wing designs were ultimately approved for prototype development: the McDonnell XF-88 Voodoo, Lockheed XF-90, Republic XF-91 Thunderceptor, and North American YF-93A, a development of the F-86, all of which flew between 1948 and 1950. After being awarded a contract on February 14, 1947, McDonnell built 2 prototypes, designated the XF-88 Voodoo. The first prototype, serial number 46-6525, powered by 2 Westinghouse XJ34-WE-13 turbojets, flew from Morocco on 20th of October 1948. Preliminary testing revealed that while handling and range were adequate, the top speed was a disappointing 641 miles an hour at sea level. After fitting McDonnell Design's afterburners to the second prototype, thrust was increased to 3,600 pounds with corresponding performance increases in top speed, initial rate of climb, and reduced takeoff distance. Fuel consumption was greatly increased by the use of afterburners, however, reducing a range. When a fly-off was held in the summer of 1950, McDonnell's XF-88A, an improvement over its 1948 prototype, emerged as the winner of the penetration fighter competition against the Lockheed XF-90 and North American YF-93. McDonnell's success was momentary, however, the Air Force, motivated by unexpected budget cuts, abruptly cancelled the XF-88A program and made the decision to use the Republic F-84E Thunderjets as interim bomber escorts. Combat experience in Korea soon revealed that the straight-wing F-84s were not suited for air-to-air role, and the North American F-86 Saberjet clearly lacked the range to escort bombers to long-range targets. Something better was needed, so SAC, determined to protect its emerging fleet of B-36s, issued new requirements for a long-range fighter in January 1951. This time, adding specifications for parallel development of photo reconnaissance versions of the new type. Lockheed, North American, Republic, and McDonnell all submitted new proposals, joined by a bid from Northrop for a long-range version of its F-89 Scorpion. In May 1951, the Air Force announced that McDonnell's entry, basically a scaled-up XF-88A upgraded with more powerful Allison J35A-23 engines, was the winning bidder. But before construction was authorized, the Air Force specified major changes aimed at improving overall range and performance, the most significant being the substitution of Pratt & Whitney J57P-13 powerplants, which required enlarging and lengthening the fuselage to carry more fuel and house bigger engines, plus extensively revising the air intakes and related engine ducting. The greater dimensions of the J57 engines required modifications to the engine bays, and modification to their intakes to allow larger amounts of airflow into the engine. The new intakes were also designed to be more efficient at higher Mach numbers. In order to increase aerodynamic efficiency, reduce structural weight, and alleviate pitch-up phenomena recently identified in flight testing of the Douglas D-55-82 Skyrocket, an aircraft with control surface configuration similar to the XF-88, the horizontal tail was relocated to the top of the vertical stabilizer, giving the F-101 its signature T-tail. When the McDonnell team, led by Edward M. Flesch, completed the final design in late 1951, the Voodoo had grown 13 feet longer and weighed twice as much as its XF-88 predecessor. The F-88 was redesignated the F-101 Voodoo in November of 1951. The F-101A would be, at the time, the largest single-seat fighter ever built, 67 feet, 5 inches long, and weighing over 48,000 pounds fully loaded. Although the wing had been slightly enlarged by increasing the chord of the inboard half of each panel, total area was still relatively small, 368 square feet, producing prodigious loading of 135.9 pounds per square foot, the highest of the Century series in original configuration. Internal fuel capacity increased from 734 to 2,341 gallons, augmented by two 450-gallon external drop tanks. Provisions were also made for an in-flight refueling, either via flying boom or probe and drogue systems to extend the plane's combat radius even further. An APS-54 search radar provided all-weather capability, and heavy firepower came from 4 20mm cannons, 3 Hughes GAR-1 Falcon radar homing missiles, and up to 12 unguided rockets. Before the final design was fixed, the Air Force expanded the fighter's potential mission uses by adding the capability to carry a nuclear weapon on an external rack. In late 1952, the mission of the F-101 was changed from penetration fighter to strategic fighter, which entailed equal emphasis on both the bomber escort mission and on nuclear weapons delivery. The new Voodoo mock-up with the reconfigured inlets, tail surfaces, landing gear, and dummy nuclear weapon was inspected by Air Force officials in March 1953. The design was approved. An initial order for 29 F-101As was placed on May 28, 1953. No prototypes had been required, as the F-101 was considered a simple development of the XF-88. with the Cook-Craig production policy, in which initial low-rate production would be used for testing without the use of separate prototypes chosen instead. Not surprisingly, a decision was made to limit production to the initial procurement until military acceptance testing and evaluation was well underway. The first F-101A was completed in August 1954 and shipped to Edwards Air Force Base, where its maiden flight was on September 24th, with McDonnell test pilot Robert C. Little at the controls. Early testing indicated impressive performance, a top speed of Mach 1.54, an initial climb rate of 44,100 feet per minute, a service ceiling of 49,450 feet, and a maximum range of 2,186 miles. It also revealed aerodynamic flaws that were serious enough, in May 1956, for the Air Force to halt production pending resolution of its concerns. The most serious problem was a treacherous pitch-up tendency, encountered both in high and low airspeed ranges at certain G levels with angles of attack, frequently followed by engine compressor stalls that led to loss of power or total flameout. If the pitch-up, an uncontrollable flat spin condition oscillating between 20 and 70 degrees nose-up, occurred below 15,000 feet, Voodoo pilots were under standing orders to eject. The pitch-up problem was substantially remedied by installing a pitch inhibitor, would not allow the stick to be pulled past specific points at specific speeds, and the intakes and engine ducting were redesigned to diminish the possibility of compressor stalling. After what amounted to approximately 2,000 engineering changes, the hold order on F-101A production was finally lifted in November 1956, and the type was accepted for operational service in early May of 1957. Development and testing of the photo reconnaissance version, the RF-101A, followed the fighter version by about 18 months, but due to the setbacks in the fighter program, the photo recon versions entered the operational service at virtually the same time. The aircraft was fitted with an MA-7 fire control radar for both air-to-air and air-to-ground use, augmented by a low-altitude bombing system for delivering nuclear weapons, and was designed to carry a Mark 28 nuclear bomb. The original intended payload for the F-101A was the McDonnell Model 96 Store, a large fuel/weapons pod similar in concept to that of the Convair B-58 Hustler, but was cancelled in March 1956 before the F-101 entered service. Other operational nuclear payloads included the Mark 7, Mark 43, and Mark 57 weapons. While theoretically capable of carrying conventional bombs, rockets, or Falcon air-to-air missiles, the Voodoo never used such weapons operationally. The RF-101A made its first flight in June 1956, and differed from the fighter mainly in carrying 150 gallons of additional internal fuel and having a Lathan nose that housed 3 vertical and 2 oblique Fairchild cameras in place of the search radar and 20mm guns. The RFs shared the capability to deliver a single nuclear weapon carried on a centerline rack and were marginally faster than the Fs due to the reduced weight. F-101As became operational in May 1957, with the 27th Strategic Fighter Wing in their original bomber escort role, replacing their F-84F Thunderchief. However, by this time, SAC had decided to abandon the long-range fighter concept. Even with its above-average range, the Voodoo could not escort the bombers, B-36s, and by that time B-47s and B-52s, all the way to their intended targets. The F-101A's career might have ended then and there, but for the intervention of Tactical Air Command, which saw potential in the big fighter as a tactical nuclear weapons delivery system platform. Thus, in mid-1957, the 27th Strategic Fighter Wing became the TAC-controlled 27th Fighter Bomber Wing, and all F-101As were thereafter retrofitted with the low-altitude bombing system and other apparatus needed to complete their new function as nuclear strike fighters. By late November 1957, the last of the 77 F-101As had been delivered to the Air Force, 50 of them assigned to operational units, with the remaining 27 held for experimental and test purposes. F-101As served in a frontline role until 1966, after which they were phased out and turned over to the Air National Guard units. The first of 35 production RF-101As was delivered to the 363rd Tactical Reconnaissance Wing, TRW, at Shaw Air Force Base in May 1957. It was the first supersonic reconnaissance aircraft in the Air Force inventory, and, on November 27, 1957, as a part of Operation Sunrun, 4 RF-101As set a new transcontinental speed record. They flew round-trip between McGuire Air Force Base in New Jersey and March Air Force Base in California in 6 hours, 46 minutes, and 36 seconds, with an average speed of 721 miles an hour. In the mid to late 1960s, RF-101As were used as reconnaissance trainers and were all phased out of the active Air Force inventory by 1971. A few serviceable examples, following the conversion to RF-101G standards, were transferred to Air National Guard units. Pilots who flew the Voodoo were impressed by its performance, dubbing it the One-O-Wonder, but they also considered it very unforgiving. Colonel C. Robert Oz Osborne Jr. said, "The F-101 was a lady, a fantastic airplane, but touchy, very touchy. It had to be flown properly." Air Force test pilot Richard Baird echoed that sentiment. "It's the biggest by-the-book fighter I've ever flown. The Voodoo would bite you. You really had to fly it strictly by the book." And reconnaissance pilot Colonel Jonathan Gardner noted that, "The first ride, you didn't fly it, you hung on to it." The improved F-101C and RF-101C were both ordered in March 1956. The Cs were externally identical to the A models, but had strengthened airframes to accept a higher load limit, and, in the case of the fighter version, were equipped from the start as tactical fighter bombers. All of the 47 F-101Cs built were delivered to the Air Force in 1957 to 1958, serving with the 81st Tactical Fighter Wing as nuclear strike aircraft until they were phased out in 1965 to 1966. The F-101C was the fastest tactical fighter in operational service until the advent of the Lockheed F-104, and on December 12, 1957, a stripped-down example set a new world record of 1,204 miles an hour, or Mach 1.83. The RF-101C, built in greater numbers than its fighter counterpart, entered operational service in September 1957, and the last of 166 was delivered in March 1959. RF-101Cs saw wide service with the US-based 363rd Tactical Reconnaissance Wing, the Europe-based 66th TRW, and the Far East-based 67th TRW. During the Cuban Missile Crisis in October 1962, RF-101As and Cs of the 363rd TRW flew low-level reconnaissance missions over Cuba. The RF-101C was the only Voodoo variant to see combat in Vietnam. In fact, as early as 1961, RF-101Cs of the 67th TRW, operating out of Kadena Air Force Base in Okinawa, began making surveillance flights over Laos and South Vietnam. During the same time period, 45th TRS Voodoos moved to Tan So Nhut Air Force Base in Vietnam to cover operations in the south, and served as pathfinders for the first bombing mission against the North on February 8, 1965. Between 1965 and 1970, 33 RF-101Cs were lost to enemy anti-aircraft and missiles, and 1 to a North Vietnamese MiG-21. Starting in late 1967, as more RF-4Cs arrived to the takeover reconnaissance duties, Voodoos were restricted from operations over North Vietnam. They were all ultimately withdrawn from the combat zone by late 1970. Upon their return to the States, RF-101Cs were retired from active U.S. Air Force service, and many were turned over to the Air National Guard's units. In 1965, 29 F-101As and 31 F-101Cs were modified under the new designations RF-101G and RF-101H, respectively, to serve as unarmed reconnaissance aircraft with the Air National Guard units. The modification entailed removal of radar and armament and the installation of a nose cone housing cameras and new electronic components. RF-101Gs and Hs were operated by 3 Air National Guard units, the 154th TRS in Arkansas, the 165th TRS in Kentucky, and the 192nd TRS in Nevada. In early 1968, the seizure of the U.S. naval surveillance vessel Pueblo by the North Koreans led to President Lyndon B. Johnson to activate all 3 Air National Guard Voodoo units. Each served a rotational tour at Itazuki Air Force Base, Japan, and compiled impressive records, flying 19,715 tactical hours and 11,561 sorties, and exposing 841,601 feet of aerial film. The last single-seat reconnaissance Voodoos were removed from the National Guard service in 1976. The most numerically important and longest-lived Voodoo was the two-seat all-weather fighter interceptor version, the F-101B. By the end of 1953, the Air Force's ambitious two-step interceptor program with Convair, the Mach 1 F-102A, scheduled to be followed by the Mach 2 F-102B, redesignated the F-106A in 1956, was seriously behind schedule. An aircraft was needed to plug the gap between this so-called ultimate interceptor and the subsonic Northrop F-89 Scorpions, Lockheed F-94 Starfires, and North American F-86D Sabres serving with Air Defense Command. ADC's expression mission was strategic defense to interrupt and destroy Soviet bombers en route to the United States before they reached our shores. Late in 1953, the Air Force asked aircraft manufacturers to submit proposals for a new missile-armed all-weather interceptor under the classification Weapon Systems WS-217A. McDonnell offered a single or two-seat adaptation of the F-101 that would incorporate new fire control and missile systems and use more powerful Wright J67 engines, license-built copies of the British Bristol Olympus that were supposed to produce 22,000 pounds of static thrust each. The Air Force selected McDonnell's proposal in mid-1954, specifying the two-seat version, and issued a letter of intent in March 1955 for an additional batch of 28 aircraft and potential production of 68 more. The expectation was that the first flight would take place in mid-1956, and the prototype would enter the operational service in early 1958. After the letter of intent was issued, McDonnell requested the designation F-109 for the airframe portion of the WS-217A project, but the Air Force, evidently conscious of the funding obstacles associated with the new aircraft as opposed to the improvements to the existing type, called it the F-101B. Although McDonnell had the F-101B mock-up ready for inspection by September 1955, the entire Voodoo program was put on indefinite hold while the aforementioned aerodynamic problems with the F-101A were being ironed out. Further delays and uncertainties with the J67 engines led to a decision to use Pratt & Whitney J57P55 power plants, which featured longer afterburners and a thrust rating of 16,900 pounds per engine. The F-101B shared the center and aft fuselage sections and tail group of the F-101A series, and, other than bulged wheel well doors to house larger tires, the same wing platform. But the F-101B introduced a completely new, 4-foot longer forward fuselage section with a tandem cockpit layout for the pilot and radar operator. Also new was a Hughes MG tracking and fire control system, essentially an upgrade of the E6 system already utilized in the F-89D, and a rotary weapons bay that held 4 Hughes Falcon semi-active radar and infrared missiles. The first F-101B took off from Lambert Field in St. Louis on March 27, 1957, a year behind schedule, and the Air Force spent nearly 2 more years conducting extensive tests and evaluations before releasing the Voodoo interceptors to operational service. Flight performance met expectations, a top speed of Mach 1.66, a combat ceiling of 51,000 feet, and a normal range of 1,387 miles. But the F-101B had other problems that seriously hampered its operational effectiveness. The radar operator's position was poorly designed, and little could be done to improve it other than minor adjustments. Even more worrisome, the MG-13 fire control system did not adequately control the weapons on a platform as fast as the F-101. A proposal to replace the system with the more advanced MA-1 developed for the F-106 was rejected because of the cost involved. Deficiencies notwithstanding, the F-101Bs became operational with the 60th Fighter Interceptor Squadron at Otis Air Force Base in Massachusetts on January 5, 1959. On the plus side, the two-seater Voodoos had been extensively tested by the time they had reached ADC, and they finally gave the Air Force an interceptor capable of advanced performance at affordable cost, $1.7 million per plane. compared to $4.7 million for an F-106A. By the end of 1960, no fewer than 17 ADC squadrons were equipped with F-101Bs. Production ended in March 1961, with a total of 480 aircraft delivered. Beginning in 1959, McDonnell undertook a modification in which approximately 1 out of every 4 F-101Bs would be fitted with dual controls while retaining full ADC mission capability. Used for conversion in operational training under the initial designation TF-101B, these aircraft were redesignated F-101Fs in 1961, after 79 examples had been modified. Late production F-101Bs boasted upgraded fire control systems and the ability to carry 2 nuclear-tipped, unglided Genie MB-1s or Air-2A missiles in place of the 2 Falcons. In a modernization program, Project Bold Journey, completed between 1963 and 1966, most F-101Bs were fitted with infrared sensors to facilitate tracking of hostile aircraft regardless of radar jamming, and also received a much improved pitch control mechanism that functioned through an automatic flight control system. F-101Bs/Fs began to be phased out of Air Force service in 1969, without having fired a shot in anger, and the last active duty squadrons operating the type, the 60th and 62nd FIS, retired their Voodoos in April 1971. Simultaneously, F-101Bs and Fs were delivered to the Air National Guard units, starting with the 116th FIS, Washington ANG in November 1969, and ultimately went on to fully equip 8 fighter interceptor units in 7 different states. The Air Force retained a small number of F-101Bs after 1971 for fighter interceptor training, and the last of those was retired in September 1982.
Speed, climb, range, firepower. They're all wrapped up in this new penetration fighter. Fast enough, maneuverable enough, destructive enough to crush enemy air forces and destroy tactical air targets on long or short missions. An airplane designed for quick and easy maintenance so that it can strike and strike quickly again and again. These are the qualities conceived by the Air Force. These are the qualities that McDonnell and Air Material Command engineers have designed into its every component part. Now undergoing intensive flight tests at Muroc Air Force Base, the first XF-88 prototype has already equaled or surpassed every guarantee made by the manufacturer. It has actually demonstrated excellent aerodynamic characteristics at all speeds. To substantially improve climb, high speed, and takeoff, the number 2 XF-88 has been equipped with afterburners. It is capable of demonstrating in flight performance closely approaching the afterburner-equipped production airplane. The performance of the production airplane is carefully estimated and coordinated with flight information by key McDonnell engineers who have compiled data such as this graphic illustration of the F-88's radius of action of 1,200 statute miles. For this mission, fuel is provided for the takeoff and climb to best cruise altitude of 40,000 feet. The airplane then cruises out at 570 miles per hour to a target 1,200 miles from the takeoff point. Combat occurs over the target at 35,000 feet for 20 minutes, including 5 minutes of afterburner operation. Level flight speed available at this altitude is 656 miles per hour. Finally, the F-88 returns home at its best cruise altitude of 45,000 feet and arrives over home base with reserve fuel for 30 minutes at 5,000 feet. When used for interception, an altitude of 50,000 feet is reached in 6 8/10 minutes from a standing start. When undertaking ground attack missions, the 88 packs the lethal wallop of 2 1,000-pound bombs and 8 5-inch HVAR rockets, in addition to the normal armament of 6 20-millimeter cannon with 1,500 rounds of ammunition. For such missions, the F-88 can deliver an attack with rockets, bombs, and guns on a ground target located 635 miles from the takeoff point and never at any time exceed an altitude of 5,000 feet. Tactical conditions permit, this same destructive attack can be delivered on ground targets located over 900 miles from the takeoff point by allowing crews to and from the target at high altitude. And now, turning to some of the design features of the XF-88, we note that the wing is swept sharply back, at a 35-degree angle to be exact, and has a surface area totaling 350 square feet. Wing thickness is less than 8%. Like the wing, the horizontal and vertical tail surfaces are less than 8% thick and are swept back at 35 degrees. Air is fed to the engines through gently curving intake ducts buried in the wing roots. 2 Westinghouse J34 turbojet engines are mounted in the fuselage for minimum frontal area and virtual elimination of unbalanced thrust for single-engine operation. The engines are each rated at 3,000 pounds static thrust at sea level. For production airplanes, improved engines rated at over 4,000 pounds will be available. Afterburners will boost this static thrust figure to 6,100 pounds. A distinctive feature of the 88's control system is the hydraulic irreversible power units, which eliminate feedback to the pilot of the high aerodynamic forces and buffeting associated with transonic flight. The elusive quality of control feel is provided artificially, thus giving the pilot smooth control force gradients under all flight conditions. The leading edge flaps can be depressed 30 degrees to improve control near the stall, but to increase the maximum lift coefficient and thus reduce stalling speeds, both leading and trailing edge flaps are provided. The power-operated canopy may be jettisoned directly aft. Excellent visibility is provided by the transparent enclosure and the high forward position of the cockpit. The bullet-resistant windshield is electrically heated, and the entire transparent area is defrosted by hot air. To allow the pilot more rapid speed control under operational conditions, speed brakes are provided in the aft fuselage. These brakes total over 13½ square feet in area and are opened and closed rapidly by actuation of a convenient cockpit switch. Intermediate positions may be selected by the pilot. Models of cockpit instruments and controls are arranged for touch system operation. And now, having given the XF-88 a thorough grounded flight check, we turn our attention to the company which developed it jointly with the Air Materiel Command. Here, seen from the air, is the McDonnell factory on the edge of Lambert Field, consisting of plant buildings totaling over 1.5 million square feet of floor space. These facilities and the industrial team of over 7,500 people stand ready to design, develop, and produce high-speed jet fighters for McDonnell's only customer, the United States government. Nearby St. Louis furnishes a fertile source of skilled personnel. Here has been installed the most efficient manufacturing equipment obtainable for the production of aircraft. Equipment to produce the components of a single experimental airplane or of a production line model by the hundreds. But before production lines can roll, many hours of careful testing must prove the product. Here, for example, a portion of the XF-88 is subjected to a structural test, which simulates the loads actually encountered in flight. All critical components are subjected to such testing. Likewise, the armament is carefully pre-tested for conformance to specifications. A complete nose of the XF-88 has been built for live firing. The 620mm cannon are mounted symmetrically, with 3 on each side of the center line. Internally stowed rockets can be readily substituted in the production airplane if desired. Note the flush closure doors or the blast tubes, which open automatically in 1/10 of a second. These doors reduce aerodynamic drag to a minimum. And while McDonnell technicians are proving each phase of experimental fabrication, the company's top-notch engineering staff is probing new fields of development and research. A permanent engineering force of over 800 helps the company maintain its favorable reputation in the jet fighter field. And, like the manufacturing organization, the engineering staff makes use of the most modern equipment available, such as the Cornell University High-Speed Tunnel and the Southern California Cooperative Tunnel. The High-Speed Cooperative Tunnel is owned by a group of 5 airframe manufacturers, including McDonnell. In addition, low-speed tunnel testing of the 88 has been conducted at the University of Washington and Georgia Tech. Spin, free-flight, and transonic wing flow models have been tested at the great NACA laboratories at Langley Field. The performance of the afterburner has also been proven by testing in the altitude chambers of the NACA Cleveland laboratories. But without adequate and reliable power plants, the time and effort expended in designing and testing the airframe would be lost. It is therefore appropriate to turn our attention for the moment to the Aviation Gas Turbine Division of the Westinghouse Electric Corporation at South Philadelphia, where quality of product carries on a tradition of over 50 years. The excellent record of the J34 axial flow turbojet engine has been made possible by simplicity of design, thorough testing of all components, and precision manufacturing. These qualities, which are briefly illustrated by typical production scenes, are built into each and every one of these fine power plants. A final step consists of installing the afterburner, which will more than double the thrust during combat at high speed. The afterburner is remarkably short, adding only 30 inches to normal engine length. It has been developed by McDonnell especially for the Westinghouse 24C engine. The attachment of the afterburner is made quickly by the toggle latch clamp. An interior view shows both inner and outer flame holders. Engine and afterburner are installed in the test cell. There, data is carefully recorded on performance by McDonnell and Westinghouse engineers. The engine is first tested without the afterburner in operation. Then the afterburner test controls are operated. And the change in the exhaust is immediately apparent. Increase in static thrust is noted and recorded, an increase of over 35%. The water jets are provided to reduce temperatures in the test cell noise muffler. And now let's return to the XF-88 and a tour of this airplane, which deserves special attention. Quick and easy maintenance. A simulated inspection check shows how this feature has been built into the airplane. The plastic nose section, which is hinged by a single toggle latch, operates at the flick of a finger to expose the radio and radar equipment. Two simple trunk-type latches open non-structural doors on either side of the nose to expose the entire gun installation, which can be removed by only one man. Reloading all 6 guns is accomplished in approximately 15 minutes by using an electrically powered feed mechanism. Engine accessories are reached by unlatching quick-acting catches on doors under the engines, allowing swift and easy access to the compactly installed engine accessories for inspection or servicing. Engine removal is accomplished by detaching the non-structural fairings around the aft section, loosening the mounting bolts and duct clamp, and uncoupling the quick-acting plumbing and electrical disconnects. The engine can then be rolled aft along the special track built into the airplane, which allows the standard bomb hoist, equipped with a simple adapter, to be brought into place for completion of removal. It has been demonstrated that both engines can be completely removed and replaced in less than 30 minutes. A maintenance feature seldom found in stressed skin aircraft is the unusual accessibility provided for inspection and repair of control cables, electrical wires, and hydraulic lines. Access panels along each side of the fuselage are removable, revealing continuous troughs through which all cables, lines, and wires are routed from the cockpit aft to the tail section. The mechanic has merely to open the large rear fuselage door should the electrical and hydraulic mechanisms need attention. Compactly located behind the pilot's compartment, the fuel storage system consists of large bullet-sealing fuel cells, shock-mounted on rubber supports to reduce the hydraulic impact when penetrated by a bullet. The entire fuel system is automatic, requiring absolutely no valving action by the pilot during flight. Each cell has its own access door, allowing removal without the necessity of collapsing. Yes, these features should give this airplane high utilization percentages, should prove that spectacular performance can be achieved without any sacrifice in maintenance and producibility qualities. And now the big moment for every experimental airplane. Official flight test evaluation by crack test pilots of the Air Materiel Command. For the 88, it is of special significance, since this is the first of a new type, the penetration fighter. A feeling of pride is instilled in all of us who have played a part in the XF-88 of today and in laying the groundwork for production of the F-88s of tomorrow. A hard-hitting aerial weapon for a hard-hitting service. The United States Air Force.
This is the first in a series of annual films depicting the development of the F-101A Voodoo fighter plane. The period covered extends from the inception of the airplane to December 31st, 1954. A single-place, twin-engine, high-performance fighter, the Voodoo was designed to support strategic bombardment aircraft by escort and high-speed delivery of special stores on long-range intruder missions. The F-101A Voodoo was developed jointly by the United States Air Force and the McDonnell Aircraft Corporation of St. Louis, Missouri. The McDonnell plant covers 2.5 million square feet of floor area and employs approximately 13,000 people, over 2,000 of whom are assigned to the Airplane Engineering Division alone. Design of the Voodoo was based largely on aerodynamic parameters of an earlier model, the XF-88A seen here on the left. The XF-88A flight development program started at Edwards Air Force Base in 1948, and the test airplanes accumulated 527 flights, totaling approximately 458 hours. In 1949, 1950, and 1951, McDonnell engineers and pilots were busy with flight and laboratory tests of the XF-88A. Much of the data obtained were used to establish design criteria for a production version of the airplane. Of the various proposals submitted to the United States Air Force, the model F-88K was selected as the production configuration of the Voodoo. This version, equipped with Pratt & Whitney J57 engines, was redesignated the F-101A. McDonnell received a contract for engineering and tooling of the F-101A Voodoo in January 1952. The first engineering personnel were assigned to the F-101A project in January 1952. Their job was to accomplish various design changes necessary for the new production configuration. For example, the tail assembly was redesigned to include a stabilator, and the mean average thickness ratio of the wings was to be reduced from 7.8 to 6.4% of the chord. Preliminary model specifications were submitted to WADC for review and comment in February 1952. Work began on production design layouts in March 1952, and the first production drawing was released in July 1952. In July 1952, the mock-up board review was held at the McDonnell plant in St. Louis. Later, in August 1952, officers from the Air Research and Development Center at Baltimore, Maryland, reviewed the F-101A mock-up. Signing of a production contract for the F-101A Voodoo was announced on 12 September 1952. In November 1952, United States Air Force officers and McDonnell engineers reviewed the cockpit lighting mock-up of the Voodoo. In July 1953, members of the F-101A Development Engineering Inspection Team assembled at McDonnell. Mechanics are shown here demonstrating engine installation. The engines in the Voodoo are readily accessible to maintenance crews. Meanwhile, actual production of the first 31 F-101A airplanes was advancing rapidly. In the spring of 1954, the assembly line began to take shape. These airplanes were scheduled for an accelerated flight test development program, which would assure that subsequent production aircraft would be well proven prior to delivery to squadrons. In August 1954, a Voodoo airframe was installed in a 150-ton jig in the McDonnell Physical Test Laboratory, and tests were begun to determine structural integrity and to verify the structural loads analysis. Loads encountered during any phase of ground or flight maneuvering were reproduced on the strength test airframe by a complex system of static loading equipment. Continuous checks, both visual and by electrical resistance type strain gauge instrumentation, were made throughout the tests for indication of approaching specimen yield or failure and for areas of possible structural instability or weakness. The number 1 Voodoo was loaded aboard 2 Air Force C-124 Globemaster cargo airplanes and flown to Edwards Air Force Base in California on the 23rd of August, 1954. At Edwards, it was reassembled and prepared for flight. While the Voodoo was being made...
This is an F-105G, the Wild Weasel variant of the Thunderchief. The last mutation of a plane that when first produced was the biggest single-engine, single-seat fighter aircraft ever built. The F-105 was an awesomely powerful weapon, and in the skies of Vietnam, it was to become known as the one-man Air Force. The designer of the F-105 was Alexander Catvelli, chief designer at Republic and no stranger to the concept of big fighter aircraft. For he had been the designer of the World War II P-47 Thunderbolt, the biggest single-engine fighter of its day, which has been produced in large numbers and had proved itself a sturdy workhorse not only in its intended role as an air superiority or escort fighter, but as a fighter bomber in the tactical support mission. Work on Advanced Project 63, the series of design studies that led to the 105, commenced in 1951, at the height of the Korean War, essentially as a privately funded update of Republic's F-84. The 84 had been developed as a jet thunderbolt for the escort and tactical fighter bomber roles. In Korea, it proved not up to the escort role in competition with the MiG-15, but it performed well in the ground attack. The 84's straight wings were part of a very conventional overall design. And indeed, the plane's latter manifestations exhibited swept wings more appropriate to the potential speed of the jet. But with the experience of Korea to guide them and the rapid pace of technological development to compel them, the design team soon realized that they were setting out to design a completely new plane. As a team at Republic was setting out on their project, the counterparts of North American company had just received U.S. Air Force support for the F-100 Super Sabre, first of the series of planes known as the Sentry Fighters that were to cover the multiple fighter roles that perceived as the Air Force moved to supersonic capability. Starting life as a reworking of the successful F-86 Sabre, the F-100 was originally described as an air superiority fighter, but its latter variations added fighter bombing capabilities. With a maximum speed of 860 miles an hour, the Hun was USA's first supersonic fighter, and, particularly in tactical support role, was to prove valuable in Vietnam. The next plane was the McDonnell F-101 Voodoo, designed as a penetration fighter and escort fighter. The rapidity of development in aviation can be judged by the fact that, though only ordered 12 months later than the F-100, the 101 had a top speed of 1,100 miles an hour. Again, the plane developed tactical capability in its later models, and it was used extensively in Vietnam, most notably in photo reconnaissance. Third of the Sentry Fighters was the F-102 Delta Dagger from General Dynamics, an all-weather interceptor commenced in 1950. Capable of 820 miles an hour, it proved only a moderate success, but naturally was to develop to become the F-106, which had a top speed of 1,500 miles an hour. The Lockheed Starfighter, the F-104, ordered in March 1953, sought flight performance at all costs as an air superiority fighter. Basically a manned missile, the 1,400 mile/hour 104 had a checkered career, but has demonstrated amazing longevity as a tactical strike and reconnaissance aircraft. At Republic, Clark Belley's team working on Advanced Project 63. After a program that ran to 108 configurations had emerged with a design for a single-engine, single-seat tactical fighter bomber with the capacity to carry nuclear weapons in an internal bomb bay. This plane, the 105A, was given Air Force approval in September 1952, originally with the intention of mass production, but in the end only 2 were built. The 105, rounding out the Sentry Fighters, was the first purpose-designed tactical strike aircraft ordered for the United States Air Force. The perception of need for such a plane derived from a combination of Korean battlefield experience, geopolitics, and interest-service competition between the strategic and tactical air commands of the USAF. For TAC, the 105, in addition to opening up parameters of their new conventional role, brought with it the capability to carry nuclear weapons over a long range, with a corresponding rise in their prestige to rival that of the Strategic Command. The Tactical Air Command support of the 105 was to prove vital to the project as the plane went through its difficult early years. Virtually all the technology and engineering of aircraft were being revolutionized at once, in response to the myriad physical changes inherent in the transition of the age of supersonic flight, and the F-105 was to have plenty of developmental problems in the years ahead. But what made the huge fighter so special was its large internal capacity. The atom bombs, more reminiscent of drums than weapons, gave it a potency far beyond any competitor. For the F-105A, significant breakthroughs in understanding the effects of transonic drag, together with some inherent deficiencies, had already seen the design superseded. It first flew for the 3 years after the USAF go-ahead, and then by then its internal systems had changed beyond recognition. Also by then, manufacture of its replacement was underway. The third F-105 was the first of the B model. We see it here on the 26th of May 1956 as it taxis to its takeoff point for its first flight. This was the first 105 to have a power plant big enough to match its size, and major external changes had also been incorporated, chief among which was the area ruling, which had rescued the F-102 from its drag and turbulence problems. This had replaced the straight lines on the A model with a slim hip over the wing. A massive 4-pedaled air brake now dominated the previously clean lines of the engine exhaust, and there had also been changes made to the air intakes, giving the Thunderchief its characteristic nostrils. A larger tail area had increased stability. These and other changes have resulted in a plane with the capacity to double the speed of sound. Perhaps symbolically, this first flight was to be beset by almost fatal problems. It was intended that the flight be short, little more than a quick circuit. But when it came time to lower the wheels, there was no response from the nose wheel. Raising and lowering the wheels had no effect. The nose wheel would not budge. Rather than abandon the plane, it was decided to attempt a wheels-up landing, and so the test pilot set the machine down on a long, dangerous slide across the salt. Eventually, the plane came to a halt, and emergency crews converged on the site in the slowly clearing dust. The crash was more than an intense embarrassment for a project that was already being scrutinized as excessively expensive and troubled by technical problems. However, it was still possible to argue that the problems were being solved in ways that consistently improved the overall capability of the plane, and that even as simply as a test program, the 105 was revolutionizing the understanding not only of the science of aviation, but the potentiality of a tactical aircraft. The cause of the crash was soon identified in the new air intake controls, which at the high thrust settings were jamming the wheel in a position, a fairly simple thing to correct. One other thing that the crash demonstrated was something that those who flew the Thunderchief in action came to know and approve of its toughness. The plane was lifted, the undercarriage was lowered, and the prototype was towed away to be mended and rebuilt. Rebuilt, the plane rejoined the test program. As work progressed on tying together all the systems and ironing out all the bugs in the components, the engineers were dealing with concepts and forces they could only barely control, and overcoming the snags as they appeared. It's difficult to think of any other way that these problems, theoretical and practical, could have kept up with the intense scramble of technical development. In being the first plane capable of both air-to-air fighting and air-to-ground semi-automatic weapons delivery, the plane relied on avionics packages far in advance of anything previously attempted. Among these advanced facilities were radar models for air search, contour mapping, terrain following, and automatic tracking of air and ground targets even in blind conditions. Throughout its life, the 105 was to almost constantly receive new and updated facilities, but even from the first, this was a plane that was far ahead of its time. The rebuilt plane was allocated to conduct the spin testing program, a spin recovery parachute which installed on the tail of the plane. This required removing a panel to afford room for the chute and removing the air brake so that, if needed, the chute would be unimpeded. Trials on the chute demonstrated that it worked satisfactory. The aim of spin testing is to ensure that the plane can be recovered from a spin to normal flight. That, once control has been lost, it can be regained. Of course, the first thing to do in such a test is to lose control of the aircraft deliberately. Then, the test pilot sits there while his plane plummets through the air for a specified duration, and then he attempts recovery. This is not for the faint-hearted. The emergency spin recovery parachute was not needed, as the planes proved to have a natural tendency to level out after each revolution, and the pilots were able to resume control fairly easily. However, the airframe still had to be tested, and so the trials went on. "47 times the pilots let go and watched the horizon slide away slickingly as the plane commenced its fall. If you look carefully here, you'll see a pillar of flame leap from the tail of the plane as the engine stalls. Though the flight test proceeded well, the technical problems persisted, with the engine and the avionics still unreliable. The uncertainty of performance was matched by a wider uncertainty about the future of the plane. The original expectation of large production had been amended to 37, then cancelled altogether in December 1953. A reinstated order in February 1954 was for 15 aircraft. But by September, this had already come back to 3. In October, it was back to 6. Parallel for this state of flux, the operational requirements for the new fighter had already been repeatedly amended before being first published in December 1954, and, by April 1955, had been changed 3 more times. The men conducting the test series went on with their work, while uncertainty continued to shroud the future of the project. The 105's already considerable range had been augmented by the addition of external fuel tanks, and these two had to be tested to establish the effect they had on the plane, as well as to test the tanks themselves. Throughout 1957, the testing went on, with the test aircraft logging many hours over the desert as the plane was slowly sorted out through multiple modifications. The pre-service evaluations due for completion in November 1959 were to eventually go on until March 1961. Of the specifications added in 1954 was that the F-105 should be capable of in-flight refueling, another recent innovation already being widely used. With an airplane like the F-105, this was a tricky proposition. For the fighter pilot to slow down to the same speed as the tanker left him with insufficient airflow over the wings to maintain lift. The top speed of the tanker and lowest speed of the F-105 were very close, and, as you see, the fighter becomes very hard to maneuver, especially in the turbulence of the larger plane, and often stalls entirely. Attempts to alleviate the problem by handing jets to the tankers, as here to a B-29, didn't help all that much. All supersonic fighters had trouble until jet tankers raised the speed of refueling to safer levels. The test confirmed the difficulty for the pilot of the fighter, and although successful couplings were made, the system remained largely impractical. Not due to any failure of the F-105, but because of the inadequacies of the tankers. Having the drogue trail from the wingtip rather than from the tail of the plane removed the operation from the worst of the larger plane's turbulence, and facilitated matters somewhat, but the tendency to stall still remained. The equipment in use, the long drogue hose, did not make things any easier with the requirement for the pilot of the fighter to maneuver onto the drogue. Not until this necessity was replaced by a system where he simply holds position in relation to the tanker and the operator in the tanker directs the connection was refueling truly a practical affair. The F-105 was equipped with two types of refueling connectors, and these were to see a lot of use in the Thunderchief's career. Back at the end of 1954, our public must have been wondering about the fate of the 105, and their anxiety can have only been slightly alleviated by the bittersweet news that they received in February 1955. The order was lifted back to 15, with the allowance for the rest of the original 34 only if funds were available in the coming fiscal year. To add to this ambiguous news was the unsettling proviso that there'd be a fly-off against the North American company's F-107, an updated, high-powered, and re-eclipsed Super Sabre variant. Had the 107 been compared to almost any other plane at the time, it may have outperformed it. However, the 105 was a rather special opponent, and the performance of the controversial big plane was beginning to quell the doubts about its worth. The revisions of the Thunderchief specifications had continued in a stream of expansions of its system's capability. Constant electronic elevations proceeded throughout the plane's development and its operational lifetime, continuing to maintain the F-105 at the forefront of performance. The plethora of design changes meant that the first 15 F-105s produced represented 5 distinct subtypes. Eventually, there would have been 19. During the test program, of course, the revisions of the plane meant that the trials were regularly extended. The normal flight testing programs were consistently completed with little trouble, as the airframe behaved very well and had admirable flight characteristics. However, the electronics of the newly conceived and developing systems caused continuing delays as their performance was lifted to their supposed specifications. With the benefit of hindsight, we can appreciate what a fine aircraft was evolving in the process. But at the time, eyebrows were being raised as there was considerable skepticism about the plane. On the 28th of May 1958, 3 years later than originally expected, the USAF took delivery of its first operational 105. Fittingly, it was the only one of its subtype. The Air Force pilots had been disappointed to hear that their new mount was in fact a rather large bomber, and had christened the plane in advance rather disparagingly as the Lead Sled, Thunder Thud, or Plane Thud. Now, they got their hands on it for the first time and immediately changed their minds, and Thud in particular came to mean F-105. But no longer in any derogatory sense. The big plan was to be universally popular with those who flew them. Not only did it handle and perform as a fighter, but it packed a combination of punches that was truly awesome. Fully laden, a 105 could carry 14,000 pounds of a very wide range of external stores, including all normal bombs, rockets or rocket pods, cannon pods, electronic countermeasures, packed air-to-surface missiles, and Sidewinder air-to-air missiles. But almost as the reason for its existence, the Thunderchief also had a bomb bay. To minimize supersonic drag, the bomb bay doors retracted neatly into the plane. To control the ejection of the bomb, both for accuracy's sake and to ensure the bomb was clear of the aircraft, it was pushed down with a pneumatic rack. The rack was strong enough to be used as a jack to load the bay if there was no bomb trolley available in wartime operations. However, the Thuds carried very few bombs internally. Most of the time, the bomb bay was occupied by a further reserve of fuel on the outer wing. There was a provision for 2 stores pylons to be fitted. These could be used to carry weaponry and fuel in any desired combination, or removed to allow the attachment of specialized delivery racks for other armaments, like this installation for the Sidewinder. The standard build and armament for all Thunderchief variants was a General Electric M61 20mm multi-barrel gun. This gun fired at 6,000 rounds per minute and could fire off the entire 1,029 shells it carried in less than 11 seconds. Air Force deliveries continue with the 335th Tactical Air Squadron, becoming the first fully equipped with the new fighter and celebrating by setting a world speed record. In 1961, the first overseas deployments were made to bases in Germany. Far away from Europe, the summer of 1964, so the Thud goes into action for the first time. Soon, they were sporting new camouflage as they were deployed in larger numbers to bases in Thailand and South Vietnam. From those bases, they launched the campaigns that were to write their name into history. For the F-105, Vietnam was the right place at the right time. Even during their service life, up to that time there had been continued problems with reliability, and as recently as 1962, they had all been grounded. Though those problems had been ironed out, the plague of minor defects and a series of accidents had continued almost up to their first Vietnamese missions. But the Thuds in Vietnam were to earn a completely different reputation as reliable and durable airplanes. They also earned a fearsome reputation as weapons. The importance of the Thunderchief in Vietnam can be simply indicated during the first 5 years of their involvement there. They flew an amazing 75% of all USAF attack missions. If the skies of Vietnam were full of bombs, it was because the thuds put them there. From March 1965, increasing numbers of airstrikes were made on North Vietnam, predominantly directed at communications targets. The raids relied almost entirely on the F-105s. The planes would heave themselves into the air with their loads of bombs and head for a rendezvous with a tanker near the North Vietnam border. But with the level of external stores they were carrying, and the way that increasingly they had to fly flat out all the way across Vietnam rather than cruising to and from the target, the range had been cut considerably, and even with full tanks, the journeys didn't leave much to spare. Then, they flew into hostile airspace. At the beginning of the war, the North Vietnamese had only limited air defenses, and the earliest raids were relatively quiet. Soon, however, supplies on anti-aircraft artillery, surface-to-air missiles, and MiG fighters began to multiply, and the raids were flown into the teeth of the most intensive air defense systems ever tested in warfare at that time. Production of the 105s had been completed in December 1964. Only 78 of the B model had ever been built. The remaining 610 had been F-105Ds. The D had acquired an extended nose, accommodating all-weather navigation systems, and thus was externally dissimilar to the B. The other 143 were the twin-seat F model. It had always been expected that there would be a twin-seat version of the plane, but 2 earlier twin-seat proposals had been dropped. The Fs were to provide the stock for the later development of the last 105, the G, the Wild Weasel. The workhorse of the bombing raids was the D. The single-seaters are bounded on the bases where the work of war went on 24 hours a day. At the end of each mission, the returning pilot would confer with his crew chief about the performance of the plane and handed it over to him for service. The service record of the F-105s in Vietnam was excellent. On any given day, over 90% of the funds were ready for work. This figure was higher than the overall average within the USAF, and considering the complexity, workload, and relative scarcity of the big planes, it's all the more outstanding to keep them in the air. Facilities for total maintenance of the planes were built at the bases they flew their missions from, and specialist teams were constantly available to fly in to handle specific problems. Teams of ground crew at the bases carried out the normal turnaround routines, like refueling, filling the water tank in the tail for the afterburner, rearming the plane, and other servicing required between missions quickly and efficiently. The The body of the plane was a patchwork of hatches, allowing access to the equipment inside. The big fuselage had very little spare room inside it, but the layout was good enough to ensure that servicing was relatively straightforward. The bases were a far cry from the mud and improvisation of the Second World War. A Thunderchief parked on Tackley's acres of hearthstand could be serviced with relative ease. The wing point combinations for the next missions were selected and affected, and the plane armed in the smooth and practice routine. A large part of the bombs that were dropped on Vietnam were iron bombs of the Second World War. Vintage, sadly, they were a part of a design philosophy and era that should have been long gone. However, modern smart bombs were not to really arrive in Vietnam until the F-111s used them in the last phases of the conflict. So the F-105 missions were often flown to deliver hardware that was uncontrolled in flight, often unstable in trajectory and sometimes unreliable in effect. But with these bombs, the thuds hammered the North and in most instances destroyed their allocated targets right through the night. The bases were a hive of activity. At the work of repairing, servicing, and arming the planes went on. Another factor that makes the 90% availability of the thuds even more impressive was their toughness. They kept coming back from missions with major battle damage to repair. Thuds sustained strikes from SAMs as well as AAAs and mid-cannons and still survived. This one has actually survived a hit from a Sidewinder. Each morning, the one man's air forces waited ready. In March 1965, the USAF flew the first of the Rolling Thunder series of strikes. The inclusion of the reference to Thunder is fitting, as throughout its 3 years, Rolling Thunder was to be the almost exclusive province of the Thunderchief. The fuller extension of the air war into the North had 3 purposes. First, to reduce the infiltration of the South. Second, to give pause to the communist leadership in Hanoi. And thirdly, to bolster the morale of the Southern leadership and the people of South Vietnam. As the name implies, the strikes rolled forward into the North, targets being progressively further and further over the border, and the thunder was real. The damage to the North's bridges and railways and roads extracted a great cost on the communists and hampered their war effort considerably. However, though at times apparently shaken, the Hanoi leadership did not break. The thuds flew in on their deadly missions, and the Vietnamese tried with everything the Russians and Chinese could give them to knock them from the sky. North Vietnam was not an ideal target for a sustained bombing campaign. There was little industrial infrastructure to damage and almost no war production. The country had an agrarian society, predominantly rural and dispersed. The few major targets in the terms of docks and storage were within the exclusion zones around Hanoi and Haiphong, the two major cities. For political reasons, these areas were not bombed for most of the war, as the US consistently tried to negotiate an end to the fighting. The Thud pilots learned their own ways of coping with the streams of sands that rose of them, splitting and diving to confuse and evade the missiles. Entangled with the MiGs, the 105s came off well. They had such reverse of power that if a MiG managed to get in position to fire, they could in most cases simply accelerate away from them further. The Thuds were capable of turning the tables on their attackers and really mixing it up. 28 MiG-17s were down by 105s. The bombs continued to rain down on Vietnam. Supporting the bombing was an electronics and communications network of unprecedented technical sophistication. Operations controllers directed a huge fleet of varied craft in the air at enemy level, from artillery spotter planes to B-52s. They dispatched rescue operations for downed pilots and coordinated the activities of tankers, bombers, and fighters. Off the coast of North Vietnam prowled the Big Eye planes packed with sensitive radar and alert for the slightest activity from the mid-squadrons. Any appearance of the MiGs was monitored and the information relayed to the fighters in the area. The constant observation, coupled with the air superiority of the Phantoms and Thunderchiefs, served to ensure that for the large periods of the war, the Communist Air Force stayed on the ground, pragmatically accepting that they could not compete. The controllers and their equipment directing the airstrikes were themselves part of a chain of command that stretched back from the Vietnam through the Pacific headquarters in Hawaii all the way to Washington, where the targets were identified and authorized. At the very end of the chain were the Thuds, sending off daily with their loads. Thousands and thousands of sorties succeeded one another, with the F-105s carrying most of the load. Whether or not one questions the strategic effect of the program, it is impossible to not acknowledge the burden that the Thunderchiefs carried and the effectiveness with which they pursued their assignments. In June 1967, the first of the Thuds to do so reached the halfway point in their theoretical 4,000-hour fatigue lifetime, to be followed soon by others. The most critical fatigue concern was the strains upon the engines. The missions that the Thuds were flying were unlike anything originally envisaged. They were regularly returning at full power with afterburner for extended periods of time. The stress on the power plants was enormous. The hot sections of the huge J85 engine were particularly vulnerable to this type of treatment. Already, there had been some shortages of spares. As a safeguard, their normal engine life between changes was reduced from 200 to 125 hours. And teams of mechanics worked on overhauling the engines, testing them and reinstalling them on the planes. By August 1968, the 388th Squadron was flying Thunderchiefs with 3,000 hours under its belt. Having gone out on 500 missions, received flag damage on several occasions, and have been involved in mid-air collision earlier in the year. By October, 3 more had passed the mark. They were growing old fast. An earlier suggestion to reopen the lines and build more F-105s had been considered, then dropped. There was a replacement for much of the work already available in the Phantom, and construction was proceeding apace on their successor, a design that had been much influenced by the story of the Thud and which had reflected many of the lessons learned in its combat life, the F-111. For the time being, the Thuds were made indispensable, and they were constantly tended to maintain their status and prolong their life. The Thuds remained in Vietnam to the end. Not only the two-seater SAM suppressing wild weasels, but also the Ds and Fs with their bombs, tactical support, and electronic countermeasure systems. The Thuds were still workhorses right through to the devastating Linebreaker 1 and 2 operations that finally brought the North to a negotiation position that allowed the US to withdraw from the conflict. Their bombing had sustained the air war against North Vietnam. There was no other plane at the time that could have done the job. The bombing was fiercely pressed home, and the results devastating, particularly when they were directed against a specific industrial target, as here on this truck maintenance depot. The Ho Chi Minh Trail buzzed with activity during the bombing halts, with trucks bumper to bumper, illustrating 2 points: the wily resolve of the Vietnamese in pursuit of their aims, and the effectiveness of bombing. With Thuds about, the trucks were far more circumspect. The pilot's tour of duty was 100 missions, and the Thuds saw hundreds of pilots through their tour and home again. They were men who were undoubtedly universally glad to be out of the war, glad to have done their job and survived. However, many of them were still to miss their big machines and the sensation of howling through the air in a huge metal monster at twice the speed of sound. Captain John Piawani began growing his mustache when he first arrived in Vietnam in 1967. When he finished his 100th mission, the mustache was 12¼ inches long. On his 55th mission, his Thud was hit by artillery over the Paul Duma Bridge, near Hanoi during a bombing run. His story is typical. Not only did he hit the bridge and bring down a span, but the damaged thud brought him home to finish his tour. Some of the Wild Weasel and other specialist planes stayed with the USAF after Vietnam, but the 105s were progressively phased out and retired into the hands of the pilots of the Air Force Reserves. There were not too many of them about, and they faded rather quickly from use. The last reserve of an F-105 was on the 25th of May 1983, exactly 25 years after the accident on the first flight of the 105B. Many pilots sat in the seat of an F-105 and went through the startup process. Many owed their lives to them. Most of them consider their plane the best in the inventory. The big fighter grew from its problem childhood, and the parameters of what an aircraft could be asked to do grew with it. In an era of multiple transitions, it is an astounding achievement that so much was got right so well in one package. There were never that many of them, and their reputation is perhaps not widespread. Nevertheless, the plane was certainly outstanding.